Welcome to the Deep Dive, where we plunge into the fascinating, complex world of your source material. Today, we're tackling a question that seems, well, deceptively simple, almost childlike, really.
Yeah, it sounds basic.
But it's one that has haunted AI researchers for decades. How do you teach a machine common sense?
It's the bedrock, isn't it?
It really is. It's a journey into the very essence of human understanding, and as we'll discover, it quickly becomes far more intricate than anyone initially imagined. So this deep dive is all about what's known as the knowledge representation problem.
A big one.
Huge. Our mission today is to unpack those early, really ambitious attempts to capture the sheer messiness of human experience in a symbolic, structured form.
Trying to bottle lightning almost.
Exactly. We're going to explore foundational ideas like semantic networks and Marvin Minsky's frames, and really delve into why representing even the most basic facts about the world turned out to be incredibly hard.
Yeah, harder than anyone thought.
These struggles, as we'll see, ultimately exposed some deep cracks in that initial, purely symbolic paradigm of artificial intelligence. We've got a fantastic stack of sources here, classic AI texts that laid the groundwork, contemporary analyses reflecting on these challenges. Should be a good guide.
And look, this isn't just a history lesson for the sake of it.
Right.
Understanding these early struggles, these fundamental roadblocks that AI hit, decades ago, is absolutely crucial for grasping where AI is today, especially with the rise of these incredibly powerful large language models.
Everyone's talking about them.
Of course. And you might look at a modern AI system and wonder, how did we get from trying to painstakingly hard code every single bit of common sense into a machine?
Like literally typing in water is wet.
Pretty much. From that to systems that seem to generate it or infer it or even just mimic it with such, convincing fluency.
Yeah, how did that happen?
Today, we'll trace the roots of that profound challenge. And ultimately, this whole journey forces us to confront a fundamental, almost philosophical question. What does it even mean for a machine to know something? Because, as we'll definitely see, a computer's understanding of its own symbols is often radically different from our own intuitive real-world understanding. It's not the same kind of knowing at all. The early dream, encoding human knowledge and common sense.
Okay, let's unpack this grand vision then. From the very, very beginning of AI as a field, there was this foundational, almost audacious aspiration.
Audacious is a good word for it.
To build machines that could reason like humans. Machines that possessed what we instinctively call common sense.
The stuff we just know.
Exactly. Think of pioneers like John McCarthy. He didn't just coin the term artificial intelligence, he actually envisioned what he called programs with common sense.
He set the bar high from the start.
He really did.
Yeah.
And he wasn't merely thinking about machines that could, crunch numbers faster than any human or solve complex math equations.
No, it wasn't just about calculation.
He was imagining systems that could truly navigate the everyday world, make simple inferences, understand basic social cues, much like a person does without even thinking about it.
That's absolutely right. This wasn't just about pure computation. It was about handling the messiness of everyday situations.
Right.
Making inferences based on incomplete information, understanding context, all those things that humans just, we take them completely for granted.
Effortlessly.
Yeah. The core idea in this early phase was that intelligence fundamentally involved, and this is a key phrase, transactions on a knowledge base.
Okay.
Imagine a vast, meticulously organized library. But instead of books, it's filled with explicit facts and rules about the world. Things the machine could actively manipulate, combine, query.
A database of reality.
Sort of, yeah. And the strong belief then was, if you could just capture enough of that knowledge, if you could explicitly define enough of these facts and rules, you could build truly intelligent systems.
Just needed enough entries in the database.
Right. That was the hope. Now, consider a simple, seemingly obvious statement for you. If you want to go from point A to point B, and point B is a building, you can likely enter through a door.
Okay, makes sense. Trivial.
For us, yes, trivial. It's just embedded common sense.
Yeah.
But for a machine, each part of that statement, go, building, enter, door, even likely, needs to be represented with perfect clarity and connected in a way it can actually use to reason. It needs to know what a building is in a physical sense, what a door is, what entering implies as an action, the typical spatial relationships, the functional relationships.
All the unstated assumptions.
Exactly. All the stuff we don't even realize we know. When you break it down, trying to formalize just that one simple sentence, It's a monumental task.
I understand that automatically without thinking. But how do you give a computer that same intuition? How do you formalize something that feels so natural, so unstated, so obvious to us without literally explaining every single tiny detail? What was the fundamental approach to tackling this early on?
Well, early AI largely embraced what we call formal systems, and these are inherently digital.
Digital, like ones and zeros.
In a sense, yes, but it means more than just binary.
Right.
It describes systems designed to be perfectly precise, unambiguous, and entirely self-contained.
Okay.
And this precision, this clarity, was initially seen as an immense strength. It was a way to build intelligence on solid, logical, predictable ground.
Got it. So break down digital in this context.
Sure, self-contained meant that all the relevant information needed for a particular task, or even for understanding some slice of the world, had to be explicitly encoded within the system itself.
Nothing external.
Nothing. No reaching outside for extra context. No relying on those implicit assumptions that humans constantly make. Everything had to be right there, defined. Then there's perfectly definite. This means absolutely no ambiguities, no approximations, no gray areas, no judgment calls.
Black and white.
Exactly. Think of a simple digital switch. It's either on or off, 1 or 0. There are no in-between states, no borderline cases, no mostly on. Every element, every fact, every rule had to be binary, crystal clear. For example, if you're simulating a robot moving blocks, a block is definitely on another block, or it's definitely not, period.
No, sort of balanced precariously.
Precisely. And finally, finitely checkable. This ensured that any operation or check the system needed to perform, like, is this chess move legal, could be completed in a finite, predictable number of steps.
Guaranteed to finish.
Right. It removed any uncertainty about computational limits or endless loops. The core idea was, if we could just translate the messy world into these precise, unambiguous terms, machines could process it, reason with it, and, eventually achieve true intelligence.
That digital nature then offered this really tantalizing promise of clarity and determinism.
Yeah, predictability.
It held out the hope that if we could just articulate the world in these perfectly precise, unambiguous terms, machines would simply be able to process it, reason with it, and ultimately achieve intelligence. It even led to some pretty exciting, maybe even wild philosophical thoughts. Like the idea, maybe best articulated by Douglas Hofstadter, that the symbolic levels of the mind, basically, our thoughts, concepts, or very intelligence, could somehow be skimmed off their neural substrate.
Meaning our biological brains.
Right, skimmed off our squishy brains and then implemented in other electronic media, like computers.
Wow. So intelligence is substrate independent.
That was the provocative idea, that the underlying mechanisms of thought might be separable from the unpredictable biology of our brains and perfectly replicable in silicon. It was a very bold, very optimistic vision for the future of AI back then. 2, first attempts at knowledge representation. From logic to frames.
Okay, but here's where it gets truly fascinating, and also where the initial cracks in that grand symbolic dream really started to show.
The reality check.
You got it. A core, maybe humbling realization that emerged from these early attempts was this. A computer does not have access to the intended interpretation of its own symbols.
What does that mean exactly? The intended interpretation.
It means all the computer truly knows is its internal knowledge base, that explicit set of facts and rules it's been given. Nothing more.
Okay.
Now, if a statement is a logical consequence of that knowledge base, the computer can infer it's true. It's true in all possible logical models, all interpretations of its own KB.
Makes sense mathematically.
But, and this is the crucial but, if a statement is not a logical consequence, the computer doesn't know if it's true in the intended interpretation. The way we understand those symbols in the real world.
Why not?
Because there might be some other perfectly valid logical model of its internal knowledge base where that statement is false. It simply lacks the external human-like grounding. It doesn't understand what those symbols actually refer to in the physical or social world. It only knows the rules it was given.
So, if I'm getting this right, a computer doesn't inherently understand what a cat is in the real world. You know, that furry, purring creature that jumps on your keyboard.
Exactly. It doesn't know that cat.
Instead, it only understands the rules and relationships you've explicitly defined for the symbol cat within its database. Like, cat ISA mammal, cat has a fur, maybe cat has function per.
Right. Just the definitions.
It's like having a dictionary that perfectly defines every word using other words from the same dictionary, but you've never actually seen the objects those words refer to, or felt the emotions they describe.
That's a great analogy.
You could know all the rules of chess, every possible move, but without understanding the concept of competition or strategy in a human sense, it's just symbol manipulation.
Did this lead to systems that were, like, brilliant in narrow, predefined ways but completely fell apart outside those lines?
Precisely. That's exactly what happened. It led to systems that were incredibly brittle.
Brittle, good word.
They excelled within their meticulously defined micro-worlds, these small, simplified domains where all the rules were known. But once you stepped even slightly outside those boundaries, they collapsed because they lacked that real-world grounding, that intended interpretation. They couldn't handle novelty or ambiguity. Okay, so given this profound challenge, how did they try to formalize knowledge? Where did they start?
Well, naturally, they gravitated toward logic. It seemed like the most rigorous foundation. Researchers introduced sophisticated concepts like the logic of knowledge.
Logic of knowledge.
Yeah, it brought in operators like K, where KP means P is known.
Ah, okay. So reasoning about knowledge itself.
Exactly. This wasn't just about stating facts about the world. It allowed for the formal representation of an agent's beliefs and knowledge states within the system, differentiating between what's objectively true and what an agent believes to be true.
That seems important for common sense.
Crucial. It was a step towards modeling not just the world, but the minds within the world, or at least artificial minds. As researchers delved deeper, they employed even more complex logic systems, often based on first-order theories.
First-order logic. That rings a bell from a philosophy class, maybe?
Probably. To put it simply, first-order logic allows you to talk about objects, properties of objects, relationships between objects, and use quantifiers like for all or there exists.
Okay, more expressive.
Much richer expressive power than simpler propositional logic, which only deals with basic true-false statements. It let them talk about things like all humans are mortal or there exists a cat on the mat.
Got it.
Now, one particularly ingenious technique that emerged to handle the inherent messiness of common sense within this logical framework was called circumscription.
Circumscription. Sounds complex.
It is a bit technical, but the core idea is clever. It wasn't about adding more facts. It was about formalizing default assumptions.
Okay, like what?
Think of common sense rules like birds can fly. We generally assume a bird can fly, unless we're explicitly told it's, say, a penguin or an ostrich or maybe has a broken wing.
Right, the exceptions.
Circumscription was an attempt to encode this kind of default reasoning within logic. It tried to formalize the idea that if something isn't explicitly stated to be an exception, we assume the simplest, most minimal interpretation we assume the default holds true. If no exceptions are mentioned, assume the bird flies. For instance, if you're trying to describe how actions affect the world in logic, you might define something like posso A S to mean that action A is possible in state S.
Okay.
Or maybe R to denote that some result R is not true after doing action A in state S. But to make these useful, you also need action precondition axioms.
Rules about when actions are possible.
Yeah,
right?
exactly. Complex rules stating precisely when an action is possible. An axiom might say something like, for an action A to be possible in state S, certain preconditions, let's call them AS, must be true. Formally, you might write AS, P-O-A-A-N-E-D-A, where it just means implies.
It seems incredibly rigorous.
It sounds incredibly rigorous, and it held promise. A path to perfectly defining the world in logic. However, and here's the catch, the completeness assumption proved to be a monumental hurdle.
The completeness assumption.
The idea that these axioms could actually characterize all the conditions under which an action might lead to a particular outcome, or all the possible defaults and exceptions in the world.
Trying to list everything.
Exactly. In a complex, unpredictable world, that turned out to be practically impossible. The world is just too vast, too many variables, too many potential side effects, too many weird exceptions. You simply couldn't list every precondition and every caveat for every possible action. It was an insurmountable task.
That makes perfect sense, trying to list every rule for reality.
Yeah.
Good luck with that. So if pure logic, even with clever additions like circumscription, struggled with the sheer volume and ambiguity of the real world, did researchers look for other ways? Something maybe a bit more, I don't know, intuitive or less rigidly rule-based?
They did.
This brings us to another key idea from that era, one that still gets talked about today. Marvin Minsky's concept of frames, right?
Absolutely. Minsky's frames offered a fundamentally different approach, moving beyond just isolated facts and logical rules. His work did bring the problem of how to represent our everyday knowledge into the open in AI. in a very direct, very influential way.
Oh, so.
Instead of trying to just list everything as individual facts or rules, frames offered a way to structure knowledge around common, predictable situations, trying to mirror how we as humans seem to organize our own experiences.
Okay, structure is key. How do they work?
Frames are essentially data structures. Think of them like templates or maybe schematic diagrams designed to represent stereotyped situations that we acquire through a lifetime of experience.
Stereotype situations, like going to a birthday party.
Or, classic example Minsky used, a restaurant frame. When you hear the word restaurant, your mind doesn't just pull up isolated facts like food is served there. Instead, it instantly activates an entire framework, a frame. And this frame comes prepackaged with slots or placeholders for common elements you expect to find. Like a waiter, a menu, the act of ordering food, eating, paying a bill, even the general sequence of events like being seated first, then ordering, then eating, then paying.
Okay, a whole package deal.
Exactly. And when you then encounter a specific restaurant scenario, say you walk into an Italian place, your mind activates this generic restaurant frame and starts filling in the specific details. This waiter, this menu item, this bill amount. And crucially, it allows you to reason and make inferences even about things that aren't explicitly stated.
Like assuming there will be tables and chairs.
Precisely. Or assuming you'll probably pay at the end. This allows for incredibly rich implicit understanding, letting us make predictions and understand what should happen next based on past experience encapsulated in the frame.
That's a really powerful way of thinking about it. It feels much closer to how my brain works. It's like if someone says to you, it's raining frogs.
Okay, weird example, but go on.
Your mind doesn't just process the literal meaning of 3 words. Instead, it immediately activates a whole suite of frames, weather frames, animal frames, maybe even unusual phenomena frames.
Right.
And you instantly start making inferences. Where would frogs come from in the sky? What happens when they hit the ground? What kind of bizarre weather event or maybe, biblical plague could cause this?
Is the person pulling my leg?
Exactly. Is the speaker reliable? All of that rich contextual understanding and inference happens almost instantly, all from just 3 weird words, because your mind is activating these interconnected frames built from a lifetime of experience. You're not just processing the literal, you're contextualizing it within this huge web of associated knowledge.
Perfectly put. And while Minsky's frame idea was incredibly insightful, and it resonated deeply with how psychologists thought about human cognition, it also quickly led down 2 main kind of divergent research paths, which really highlight the inherent tension in trying to represent common sense.
Okay, what were the 2 paths?
One path was what we can call micro-world analysis. Researchers like Roger Schank and his students focused on highly specific limited domains. They called them pre-analyzed specific domains.
Like it's understanding stories about restaurants, maybe.
Exactly like that. They made explicit assumptions about everyday activities within these narrow contexts. This allowed for some impressive, albeit limited success in areas like story understanding or question answering, but only within those tightly defined bounds.
So, successful, but not general.
Right. By definition, these systems weren't generalizable to the wider, messier world. The other path was more ambitious. It was the no-tricks basic study, explored by groups like Terry Winograd and Daniel Bobrow. Meaning, their aim was to use frame structures for a broader, more open-ended character of everyday know-how. They wanted to capture the full scope of human common sense without making too many simplifying assumptions, without restricting themselves to tiny micro-worlds.
That sounds much harder.
Or it was. This second approach, while intellectually courageous, quickly ran headfirst into the monumental complexity and sheer unpredictability of the real world.
So it struggled more.
It struggled to scale and to handle the sheer variety. This divergence really reflects the core challenge of early AI. How do you achieve narrow, demonstrable success without losing sight of the ultimate, much harder goal of truly general intelligence? It was this constant balancing act, this tension between depth and breadth.
And as researchers were grappling with the complexities of logic and frames, there was another approach gaining traction, right? One that tried to represent knowledge more like a network of connected ideas, like how we might map things out visually.
Ah, yes, you're talking about semantic networks.
That's it. Semantic networks. They were also pretty foundational back then, weren't they? How did they work? What was their angle?
Yeah, semantic networks were a very intuitive and influential approach, emerging roughly in parallel with frames and logic-based systems. The core idea was really simple and appealing. Represent knowledge as a graph.
Nodes and edges.
Exactly. Nodes represent concepts, objects, or entities like cat, mammal, Felix. And the edges, or links, represent relationships between them, like ISA, has a, lives at.
Okay, visual.
Highly visual, very easy to understand. Imagine a network. You have a node for cat, another for mammal, and a link labeled ISA connecting cat up to mammal. Then you might have a node for whiskers and a link labeled has a connecting cat to whiskers.
And maybe Felix connected to cat with an ISA link.
Precisely. The appeal was immediate. They allowed for intuitive inference, especially property inheritance. If you know Felix ISA and cat has a fur, you can infer that Felix has a fur just by following the links.
Simple path following.
Right. This was a powerful way to organize taxonomies, hierarchies, attribute information, all sorts of common sense facts, interconnected. Early systems used them quite successfully for natural language understanding and question answering because they could represent sentence structures and the meanings of words in this linked way.
That does sound very natural, almost like a mind map for a computer. But if they were so intuitive and powerful, where did semantic networks run into trouble? What were their limitations when it came to really capturing common sense? Did they hit a wall too?
Oh, absolutely.
Yeah.
Despite their intuitive appeal, semantic networks face several critical limitations that stopped them from scaling to full common sense. One of the biggest was ambiguity.
Ambiguity in the link.
Exactly. For instance, what does the link labeled ISA truly mean? Does cat is a mammal mean a cat is a type of mammal, a subclass? Or does it mean a specific cat is an instance of a mammal?
Ah, the type versus token distinction.
Right. Without strict formal semantics defining exactly what each link type meant, inferences could become unreliable or logically unsound. This led to serious issues with inheritance.
Like?
Well, if a specific cat, say a sphinx cat named Sphinxy, as a cat, but Sphinxy is explicitly hairless, how do you correctly override the has a fur property inherited from the general cat node?
Right, you need exception handling.
You need robust exception handling, otherwise you get contradictions. It required adding complex rules or ad hoc mechanisms on top of the simple network structure. Another major hurdle was quantification. Semantic networks really struggled to represent statements involving all or some.
Like all birds can fly versus some birds can swim.
Exactly.
Yeah.
Representing those kinds of distinctions, universal versus existential quantification, requires more sophisticated logical constructs that simple node and link networks couldn't easily handle on their own.
Okay.
They also had trouble with negation, like cats do not fly, and representing temporal reasoning, things changing over time, like the cat was on the mat, but now it's on the sofa.
So good for static snapshots, bad for dynamic reality.
Pretty much. While they were excellent for representing static hierarchical knowledge, like biological taxonomies, capturing the dynamic, uncertain, negative, and nuanced aspects of everyday common sense proved to be a persistent challenge. The intuitive structure started to break down when faced with the full complexity of human language, reasoning, and experience. They just weren't expressive enough on their own. 3. The fundamental difficulty. Why common sense is so hard to represent. So we've seen logic-based systems hitting walls, frames facing their own challenges, semantic networks running into limitations. What does this all mean for that ambitious dream of encoding common sense?
Sounds like it was harder than expected.
Way harder. One of the deepest cracks that emerged in the symbolic AI paradigm came from what researchers started calling the epistemological problem.
Epistemological, relating to knowledge itself.
Exactly. It became painfully clear that without an incrementally expandable knowledge base, any AI model is essentially prevented at the outset from growing toward an intelligent mechanism.
Meaning it can't learn.
Precisely. You simply couldn't pre-program everything, load it up once, and expect it to scale or adapt. True intelligence, particularly common sense, isn't a fixed, static database that you just fill up. It's a dynamic, evolving understanding that continuously learns and adapts based on new information and experiences.
I find that incredibly insightful. It really highlights how the static nature of those early knowledge bases severely limited their ability to acquire new information, adapt to novel situations, or learn from experience in any meaningful way.
They were frozen in time, essentially.
Right. Human common sense isn't a fixed set of rules we're born with or explicitly taught once. It's constantly updated, constantly refined by every single experience we have, every conversation, every observation. The world is simply too vast, too fluid, too interconnected to be perfectly predefined in advance.
You can't anticipate everything.
We accumulate knowledge, we revise it, we integrate it almost effortlessly. That's just a fundamentally different way of operating than loading a static database.
It absolutely is. And the way we humans use language also revealed fundamental challenges that these symbolic systems really struggled to formalize. It highlighted that the uses of reference in discourse are not the same as those of naming and internal representation.
Okay, unpack that. Reference versus naming.
Think about how we talk. In natural language, we effortlessly use different expressions, maybe the mother, then later Maria, then the woman in the red dress, then just she or even it, if we're referring to an object, all to refer to the same person or thing, sometimes within the same conversation.
Yeah, we do that all the time.
We do it for efficiency, often to pick out an object with the least amount of breath, as the saying goes. We assume our listener can follow along using context. The reference is fluid, context-dependent, and relies heavily on shared human understanding. Internally, however, for a machine, each of those different natural language expressions, the mother, Maria, she, might correspond to different canonical data structures or constituent entities within its knowledge base.
Different internal labels.
Potentially, yes. A computer can't just magically infer context or speaker intent like a human does. It needs explicit, linked representations for every possible way an object might be referred to. And, crucially, it needs a robust mechanism to connect all these disparate references back to a single underlying real-world identity.
Resolving pronouns and descriptions.
Yeah, exactly. Co-reference resolution. This is a much deeper problem than just parsing the grammar of sentences. It's about the very nature of identity and reference in a machine's internal world versus how we casually express it. For us, context disambiguates. For the machine, context is the problem it needs to solve explicitly.
Now, here's where it gets really interesting and maybe a bit humbling even for our own human understanding. Even predicting the effects of seemingly simple action stuff we'd consider straightforward common sense turned out to be incredibly hard for these symbolic systems.
Oh, yeah. The world is full of surprises.
Take a teacher, for instance. A human teacher, even a highly experienced one, may not know the effects explaining a concept, even if the state of the students is known.
Right. You give an explanation.
And you can't always predict exactly how each student will react, what they will actually learn, if they'll misunderstand something completely, if it connects with what they already know. No matter how well you think you understand their current state or background knowledge, the world and people just aren't fully deterministic.
This point about effect uncertainty is absolutely critical, and it leads directly into one of the most notorious problems in early AI, the frame problem.
The frame problem, related to Minsky's frames.
Related in spirit, but technically different. The frame problem in this context asks a fundamental question. When an agent performs an action in the world, what changes as a result, and just as importantly, what stays the same?
Ah, okay. That sounds simple, but I bet it's not.
It's profoundly difficult. In many real-world scenarios, it's inherently hard, maybe impossible, to predict the exact deterministic outcome of an action. If you push a block across a table.
Its position changes.
Right. Its position changes. Its color probably doesn't change. Its weight doesn't change. Its relationship to other blocks might change. But what about the dust motes on the table? What about the air currents? What about the temperature of the block due to friction?
Oh, wow. Okay.
Explicitly stating everything that doesn't change after an action, all the non-effects, is computationally intractable. The world is infinitely complex. You can't list everything that stays the same. So the best an agent can often do in such situations is to assign a probability distribution over the effects, to say maybe this action has a 60% chance of resulting in state X, a 30% chance of state Y, and a 10% chance of some unexpected state Z.
Moving from certainty to probability.
Exactly. And this is a significant departure from those perfectly definite digital systems we talked about earlier, where everything was binary and certain. It introduces a level of fuzziness, uncertainty, non-determinism, things that purely symbolic, rule-based AI struggled immensely to incorporate naturally.
So logic wasn't built for probabilities, really.
Not easily, no. And if you can't accurately predict outcomes, or even fully define what constitutes a change versus no change, this raises a massive question. How can you possibly plan effectively? How can you make reliable decisions in a dynamic world?
Yeah, planning seems impossible without predicting results.
Think about a simple task like making breakfast. You crack an egg, you assume the yolk won't explode, the shell won't shatter into a million pieces, the pan won't melt. You rely on countless default assumptions about what won't happen. Formalizing all that is the essence of the frame problem. The world is just too unpredictable for entirely deterministic, rule-based systems to capture fully. And perhaps one of the most profound insights to emerge from all these early struggles was recognizing what Marvin Minsky later called the single agent fallacy.
Single agent fallacy.
The idea that our belief or our knowledge is a single, stable, monolithic thing. Like we have one unified, consistent worldview inside our heads.
Which sounds plausible, but
But in reality, Minsky argued, a person's mind holds different views in different realms, often simultaneously, and sometimes even contradictory views.
different mental models for different situations.
Exactly. Our common sense isn't a singular, perfectly consistent logical entity. It's a complex, multifaceted tapestry of understanding, adapted to different contexts and purposes. He used the example of an astronomer. An astronomer can readily apply a common, everyday view of sunrise in daily life. The sun rises in the east, it gets light, it feels warmer, morning begins.
Standard stuff.
Yet at the very same time, that very same astronomer can switch gears and apply a completely modern physical view for technical astronomy problems, understanding Earth's rotation, orbital mechanics, the sun's basically fixed position relative to our little planet.
Two different models for the same phenomena.
Right. We seamlessly switch between these different, sometimes conflicting views. And which one we choose depends, as Minsky put it, upon the changing balance of power among our agencies, our internal mental processes, our current goals, the immediate context. Our sense of decisiveness, that feeling of knowing something definitively, often comes from actively suppressing most of our questions for practical action.
We ignore the complexities to get things done.
We have to. We simply don't have the cognitive resources nor the time to constantly consider every nuance or every possible alternative interpretation when we need to act. We make a pragmatic choice based on the context.
That's a powerful revelation about human cognition itself. It suggests our own common sense is far more dynamic, context-dependent, and less purely logical than we might instinctively assume.
Absolutely. It's messy.
And this points to a deeper complexity. What those early AI systems sorely lacked were programs which can step back and take a look at what is going on, and with this perspective, reorient themselves to the task at hand.
Metacognition. Thinking about thinking.
Exactly. Without that kind of metacognitive ability, that capacity for self-reflection and adaptive strategy, these systems were inherently limited. They couldn't adjust when their initial assumptions failed.
They were stuck in their ways.
It reminds me strikingly of that famous example of the Sphex wasp, which researchers like Douglas Hofstadter wrote about.
The digger wasp.
Right. The wasp follows this complex, wired-in routine that appears incredibly intelligent when it drags its paralyzed prey like a cricket to the entrance of its burrow.
It's purposeful.
Very. But if you, the observer, move the prey just a few inches away while the wasp is briefly inside the nest doing a final check, what happens?
It starts the whole routine over.
It mindlessly repeats the entire dragging routine from the beginning. Drag prey to entrance, go inside, check, come out. Find prey moved, drag it back. Over and over. It lacks true understanding or cognitive flexibility. It's just following a rigid, pre-programmed script.
Beautifully intricate, but brittle.
Exactly. And early symbolic AI, in many ways, often performed tasks without this genuine, adaptable understanding. It echoed the wasp's elegant but ultimately fragile routine. It could execute the steps, but didn't truly grasp the why or adapt when things changed slightly. 4. Shifting paradigms, the seeds of connectionism and statistical AI.
So as these fundamental difficulties mounted, the brittleness, the frame problem, the sheer complexity of knowledge, it became increasingly clear that the purely symbolic approach, relying on vast search spaces and explicit hand-coded rules, was hitting a wall.
Running out of steam.
Pretty much. The sheer scale and complexity of the real world led to what researchers dreaded, the exponential explosion of the search tree.
Meaning the number of possibilities grew too fast.
Way too fast. If every decision point branches into multiple options, the total number of paths to explore grows exponentially. This phenomenon became a stark warning against depending solely on the brute force of computers, even as they got faster and faster, as a compensation for ignorance and unselectivity in how knowledge was represented and used.
Throwing more computing power at it wasn't the whole answer.
It wasn't enough. Trying to exhaustively search every possible logical deduction or every combination of rules became computationally intractable, even for problems that seemed relatively simple on the surface.
That's a critical point. Even for games like chess, which seem perfectly digital, perfectly rule-based.
A closed system, right?
You'd think. But empirical studies quickly showed the limitations of purely brute force search strategies even there. While computers got faster and better at chess, it became clear that simply increasing processing speed wasn't enough to overcome the inherent combinatorial complexity, let alone achieve something like general intelligence or substitute for a lack of true common sense understanding.
Speed isn't the same as insight.
Exactly. You needed more than just raw speed. You needed smarter, more efficient ways to navigate that vast space of possibilities. Better heuristics, better ways to prune the search. This realization really started to push researchers away from the dominant idea that simply adding more rules or faster processors would eventually, inevitably lead to true AI.
Okay, so as symbolic AI was grappling with these immense challenges, other very different ideas were beginning to emerge, weren't they? Hinting at a potentially new path forward. One of the earliest of these was the concept of perceptrons.
Ah, the early neural networks.
Right, these weren't about explicitly programming rules at all. They offered a completely different vision. Machines that learned patterns by adjusting internal coefficients or weights based on data.
A radical shift.
It felt like a departure from the purely logical, symbolic paradigm towards something that felt, I don't know, a bit more biological, more about learning from examples rather than being told the rules. How did these early perceptrons work, and what promise did they hold initially? Perceptrons, first introduced by Frank Rosenblatt back in the late 1950s, were essentially very simple neural networks. The idea was to mimic, in a really rudimentary way, how neurons in the brain might learn.
Connections and weights.
Exactly. A perceptron would take multiple inputs, assign a weight and numerical coefficient to each input signifying its importance, sum them all up, and then apply a simple threshold function and activation function to produce an output, usually binary like 0 or 1.
And the learning part.
If the output was wrong compared to the desired output for a given input pattern, the perceptron would adjust its weight slightly, essentially learning from its mistakes through an iterative process. The famous perceptron convergence theorems provided mathematical guarantees that these simple systems could learn to classify specific types of patterns.
But there was a catch.
A big one, provided those patterns were linearly separable.
Linearly separable, meaning you could draw a straight line to divide the categories.
Precisely. In the input space, you needed to be able to separate the yes examples from the no examples with a single straight line, or hyperplane in higher dimensions. This was a promising start for basic pattern recognition, maybe a glimpse into a data-driven future for AI. However, their limitations quickly became, well, devastatingly apparent. While perceptrons could, for instance, learn to recognize simple, isolated geometric properties, like triangles or specific letters shown in isolation.
Like on a clean white background.
Right. They cannot detect them in more complicated context, where elements might overlap, be partially obscured, rotated, or appear within a cluttered scene. They lacked robustness.
Okay.
And then, most famously, 1969, Marvin Minsky and Seymour Papert published their book Perceptrons, which delivered a critical blow. They mathematically proved that a single-layer perceptron could not solve the simple XOR, exclusive OR problem.
XOR, I remember that from logic. True if one input is true, but not if both are true.
Exactly. And the XOR problem is fundamentally not linearly separable. You simply cannot draw a single straight line to separate the true cases 0, 1, and 1, 0 from the false cases 0, 1 in a two-dimensional input space.
Ah, that sounds like a big limitation.
It was huge. This revelation, powerfully argued by Minsky and Papert, was a major factor contributing to what many call the first AI winter, particularly for neural network research. Funding dried up. Plus, the time of convergence, the time it took for even simple perceptrons to learn, could increase even faster than exponentially with the size or complexity of the problem, making them impractical for anything but the simplest tasks.
So, promising idea, but fundamentally limited at the time.
It starkly illustrated that while they could perceive very simple patterns, they lacked the ability to handle nonlinear relationships, contextual understanding, and complex feature combinations necessary for real-world perception, let alone common sense. And this brings us to a really crucial historical contrast, one that profoundly helps us understand the current landscape of AI, especially with LLMs. Think back to Noam Chomsky's incredibly influential rationalist tradition in linguistics.
Chomsky and universal grammar.
Exactly. Chomsky viewed language as a game, a bit like chess, guided by innate universal rules that are hard-coded into the infant brain.
Born with the blueprint for language.
That was the idea. The goal for linguists, and by extension for AI researchers working in that symbolic tradition, was to infer these simple, elegant, governing, explicit rules through patient linguistic analysis. It was about finding the deep underlying grammar, the finite set of rules that supposedly apply to all human languages and, by extension, perhaps to human cognition and common sense itself. It was the ultimate symbolic quest. Find the rules. Now contrast that explicit, rule-based perspective sharply with how modern large language models, LLMs, things like GPT-4, Claude, Gemini, actually operate.
Very different approach.
Totally different. Instead of trying to discover and meticulously hand-encode explicit rules for language and common sense, LLMs are trained on large and expressive neural networks, networks with billions or even trillions of parameters.
The weights and connections.
Right, trained on absolutely massive amounts of data. Billions of words of data, often encompassing huge chunks of the internet, books, articles, gigabytes, terabytes, petabytes of text and code.
Learning from raw data.
Exactly. Their goal is not to find a set of simple, human-readable rules. Instead, it's to capture both the basic principles and their exceptions in their weights. The knowledge, the patterns, the statistical correlations, the rules, such as they are all embedded implicitly within that vast network of connections and numerical values learned during training.
So the knowledge isn't explicit rules, it's patterns in the weights.
Precisely. This is a fundamentally different approach to knowing. It's not about rules written by humans based on linguistic analysis or logical deduction. It's about incredibly complex statistical patterns and associations learned directly from unimaginably vast amounts of data. The common sense, if you want to call it that, the ability to answer questions plausibly, generate coherent text, summarize, translate, seems to be an emergent property of these statistical patterns, not an explicitly programmed set of instructions based on symbolic representation.
Wow. So this paradigm shift fundamentally changes how a machine knows or understands, or at least appears to.
Absolutely.
It moves from attempting to meticulously hard-code common sense into rigid, perfectly defined symbolic structures, logic, frames, networks, to learning complex patterns and associations from vast and messy amounts of real-world data.
From rules to statistics, in a way.
In essence, it's approximating common sense, often convincingly, without explicitly representing it in those old symbolic ways. And this profound change really exposes the deep cracks in that initial symbolic idea, the dream that all intelligence, all human understanding could ultimately be reduced to clear, definable symbols and explicit logical rules. The world, and perhaps even our own minds, simply proved far too nuanced, too messy, too statistical, and too unpredictable for that perfectly defined, deterministic approach to fully capture. Outro. What an incredible journey that was, diving into the heart of AI's foundational challenges. We've traced that early, really ambitious dream to encode common sense.
A noble goal.
Definitely. We explored the intricate mechanics, the ingenuity, but also the eventual limitations of those early symbolic attempts, logic-based systems, semantic networks, Minsky's frames.
All brilliant ideas in their time.
Absolutely. And we've highlighted why the inherent messiness, the uncertainty, the sheer unpredictability of the real world, and maybe even the multifaceted nature of human cognition itself made that initial symbolic dream so incredibly elusive.
Yeah, reality bites.
The struggles to define and represent even seemingly simple concepts like going from A to B or what a cat is really reveal just how profoundly complex common sense truly is. It's not simple at all.
And while modern AI, especially these large language models, has indeed found revolutionary ways to appear intelligent, to exhibit behaviors that look remarkably like common sense.
Sometimes astonishingly so.
Right. Doing this through sophisticated pattern recognition and statistical learning over these vast data sets, it raises new, maybe even deeper questions for you, the listener, to consider.
Like what?
Well, are these systems truly reasoning in a way that mirrors human understanding with actual grounded meaning behind the symbols they manipulate? Or are they just exceptionally good, statistically driven prediction machines, predicting the next word or token based purely on the patterns in their training data?
The stochastic parrot idea.
Exactly. Is it maybe a category error, a fundamental misunderstanding of their underlying nature and mechanisms to attribute human-like thinking or understanding to them? Can mere prediction, however sophisticated, however complex, genuinely become reasoning? Or is there still a qualitative leap, some form of deeper understanding or grounding that remains elusive?
Which brings us right back to our starting point, but maybe with a richer, more nuanced perspective. If, as our sources today suggest, our own common sense isn't some single, stable, logical entity,
But more like a messy toolkit.
right, a conditional, multifaceted tapestry of suppressed questions and context-dependent views, then how much do we truly understand its underlying mechanisms in ourselves?
That's the million-dollar question.
And if we don't fully grasp how we ourselves achieve common sense, how we navigate ambiguity and make default assumptions, decide what to believe or how to act in any given moment, can we ever truly expect to replicate it authentically in a machine, regardless of the technological paradigm, symbolic or statistical?
A humbling thought.
It really is. What does this uncertainty about our own intelligence mean for our very definition of intelligence itself, both human and artificial? Something to definitely chew on as you go about your day.